jaws, so we can test the ribbons. We can also test metal test sections, which are different shapes. We can put different sensing units and different clamping units onto it for different types of materials. So the last time it was actually used by a local inventor who was developing a rope system for a boat. So it's a mooring system that allows you to tie a boat up, but the rope is designed to extend at a certain force and like unravels. And it was a safety feature for when like the tide goes out, if there's a massive drop in the dock, it means you don't have boats hung in certain places. And he actually used this to work out the different force properties of his different tie methods for that rope, and he's actually developing that currently, which is quite interesting. So, engineering doesn't use this very often anymore because we don't teach the unit that it relates to, but hopefully you guys will get a bit of practical experience with it today.
Great. Right, we've got 3 different polymers. We've got polystyrene on this, so we've got 4 altogether.
So what polymer are we going to start with?
So if we start with polythene. So this is the refuse bag. Yeah.
Okay. So I'll demo how we put this in, how we set up the units, and then once I've set up one, I think you guys can have a go setting it up yourself, putting it in, working it out. So it's a very expensive piece of equipment, but only because it's so highly calibrated, very precise forces, and it's got lots of complex sensing units, none of which we'll be using. But the principle of it's really simple. You clamp in a piece of material, and it pulls it, and then it breaks. So what you do is you just place in one of the jaws.
Yeah.
So I'll take that off then.
What do we need? What is this?
So, Carl, roughly how much would this piece of equipment cost?
If you were to replace it now, probably about 50 to 60,000 pounds.
Keep it close. Christmas present. What? No, why?
Did you catch that, guys? 50 to 60,000 pounds.
I don't want these.
So what I'm going to do now is, now I've secured in the ribbon, is I'm just going to jog the machine, so it's going to move very slowly, and once I've after the tension's correct, then we can reset the force of the extension, and then we'll start the test from there. Not if we move it manually, I think it's very, very slow.
Do you want to get a wee bit closer? Are you close up? Have you got a close up?
Yep.
So you can come in closer if you want. It's not going to explode. It's not going to do anything too violent. So I'm just going to reset the force by pushing F1 and reset the extension. And what this is going to tell us now is the maximum force applied and then the distance travelled before the breaking point. So you see it's currently extending, stretching out. So we had huge extension on that, 107.988 millimeters of extension.
107.
But the force applied was 5 newtons, so really low force. So what we're doing now is returning it to the previous set position. You guys want to keep the...
Yeah.
This row, it does stop there, we go. I'm going to crash into myself. So who wants to set up this next piece?
Volunteers?
Any volunteers set us up? Can't really get it wrong.
I'm a cameraman.
Go, Jensen.
No one?
Scared them off.
Yeah.
Yeah, it's what Richard, you could do it.
Yeah.
You could do that. Pop your glasses on.
As I said, we'll just place it in the drawer, so if you just want to do this up, keep Christmas volunteers. So the other way? Yeah, so clockwise, isn't it? Until you feel it get tight. And do the same on the top. The other way. I don't know if that is. Tell you now. Just make sure it gets tight. So all we're doing is just securing the material. So there was So I'm just going to jog it now because this has got a lot of slack in there. Just moving it apart really slowly until that starts to get tight. And a reset to 0. 4. Okay. So what material is this?
This is high density polyethylene.
So HDPE.
Can you spell it?
Still going. Still going. Okay,
Hey.
okay.
So why does this need to be stronger material? What did we use it for? For the milk cartons, yeah? So for a milk carton you need something that's not going to just suddenly break as soon as you add 2 pints of milk. It needs that extra tensile strength. Okay, so we've got one more.
So if anyone's taking notes of this, it was 55 newtons was the maximum force applied, with an extension of 205.919 millimeters.
Have we got that one? We got one more sample. No, we've done that one, Daisy. So this is just simple plasticized polyethylene.
Just doubled up. What polymer is that?
Polyethylene. Polythene. Yeah, well, they've got some results, and we're going to get that picked up with it. Because you're going to do the others on the rig with the, yeah?
Let's see how this goes. So 18 newtons of force. But the force supply would really have to be half because it's double that. And then an extension of 96.485 millimetres. So definitely the weakest of the three materials.
Brilliant. And can we just try the polystyrene for the last one?
Sure.
Great. So here we've got, this is polystyrene. This is quite hard and rigid. Yeah. Right.
So a much thicker test strip as well. So taking the full force like that. Right.
Yeah.
Whoa.
So that, contrast that to the other ones.
Obviously much larger surface area, and it was able to withstand 688 newtons. So the force applied to it was far greater, but the extension was only 18.768 millimeters.
So you need to think, when we use polystyrene, where do we use it? Yeah, when we want really lightness and we want strength. So you're looking to apply that to your the purpose of your polymer now. That's great. Thank you very much indeed.